P. Jansi Nikita, EC B section. My subject about signals and systems. Let's see signals and systems. In signals and system, we have discussed singularity functions. In signals and systems, singularity functions are a set of basic building blocks, the unit step, unit impulse, and ramp functions that have discontinuous values or derivatives at specific points. In unit step and unit impulse functions, we have two different values, continuous and discrete type of values. Next, we have discussed unit step function. It is denoted as u of t, a function that is 0 for negative time and 1 for positive time. This unit step function has both positive and negative values are given. Purpose models a switch that turns on at t equal to 0, making a single or voltage appear or change its state abruptly. Next, unit impulse. Unit impulse function, it is denoted as del of t, also called as Dirac delta function. Let's see definition. An infinitely high, infinitely narrow spike at t equal to 0 with an area of 1. Unit impulse means area is 1. Purpose represents an instantaneous event such as a sudden brief change in a signal and is the derivative of the unit step function. This unit function is the derivative of a unit step function. Let's see diagrams. Unit impulse function. This is the diagram of unit impulse function. Infinitely, this is 0 to 1. Next, unit step function. U of t, it is denoted as U of t, means 0 to U of t, 0 to t time period. Next, closed or complete set of orthogonal functions. A closed or complete set of orthogonal functions is an orthogonal set where any function in a given space can be represented as a linear combination of the functions in the set, resulting in 0 mean square for the representation. In other words, if a function exists, closed or complete set of orthogonal is the mean square error for the representation of a function. Next, orthogonal function means a set of functions phi of k of t is orthogonal over an interval if the integral of their product is 0 for any distinct pair of functions, that is phi I of t, phi j of t dt equal to 0 for I not equal to j. Set of functions means phi of k of t is a orthogonal over a interval's integral of product is 0. Next, complete set. A set of function is complete if it can be used to approximate any arbitrary function in a given space with 0 error. This is also known as closed set. Means set of functions is complete, approximately function in given space with 0 errors. Until this means no errors is occur. Mean square error for a function f of t and an orthogonal set phi of k of t The mean square error is the integral of a square of the difference between FFT, its approximation using orthogonality. For a complete set, this error can be made zero. Previously, we have discussed non-zero errors, but these are zero errors. This is mean square error. Difference between approximate using orthogonality. For a complete set, this is the error can be made zero value. Next, orthogonal functions. Two functions f of t and g of t are said to be orthogonal over an interval a comma b with respect to weight function w of t. If these limits are having integral a to b f of t g of t omega of t dt equal to 0. These orthogonal functions have examples and over 0, 1 when n is not equal to m. Polynomials Pn of x over minus 11 with weight w of x equal to 1. This is the examples for orthogonal functions. Next, orthogonal set. A collection brackets of f1, f2, f3 and so on is an orthogonal set if every pair of different functions is the set is orthogonal. This collection of orthogonal set, every pair of different functions are orthogonal sets. These limits are integral a to b fm of t fn of t w of t dt equal to 0 for m not equal to n. Also integral a to b fn square of t w of t dt equal to 1. This is also represent this notation. Then the set is the orthonormal. This is the orthogonal set. This is orthonormal set. Next, closed or complete orthogonal set. A set of orthogonal functions is called complete. Means set of all orthogonal functions is the complete set. If any function g of t that is square integral over a comma b can be expressed. Linear combinational possibility infinite. These have the intervals of a comma b of the set functions. That is g of t equal to summation n equal to 1 to infinity cn fn of t, where the coefficients cn are determined by projection. Means g of t equal to summation n equal to 1 to infinity cn fn of t. Next, formula for orthogonal set. Cn equal to integral a to b g of t fn of t w of t dt by integral a to b fn square of t w of t dt. This is it is the formula for orthogonal set. Next, examples of complete orthogonal sets. For Fourier series basis on the intervals of minus pi comma pi. Any piecewise continuous periodic function can be represented as the intervals of minus pi comma pi. Polynomials Pn of x complete on minus 1 to 1. These polynomials are the intervals of minus 1 comma 1. Hermite polynomials complete on minus infinity comma infinity with Gaussian weights. Next, Bessel functions form complete sets in cylindrical coordinating problems. This is all about in your signals and systems. Singularity functions and closed or complete set of orthogonal functions. In singularity functions, four types are there: unit step, unit impulse, and unit ramp signals can be used for singularity functions. In closed set or complete orthogonal functions, we have discussed so many examples and formula for orthogonal set. Orthogonal set means non-zero errors are present, but mean square errors means non-zero errors. Zero errors are present. This is the difference between orthogonal set and mean square error. These all are about these two topics. Thank you.